Okay, so your lab number 5, just don't forget it's due next week. Please check the exact deadline on the PDF. It's really the latest time I can push forward, but I'm pretty sure you got enough time. But don't forget to really complete lab number 5, you want to do at the same time the background study on abstract classes and interfaces. So they are still, built upon the notion about expectation and also about ancestor descendants. So it shouldn't be too difficult for you to go over. Again, I got slides, notes, and also videos for you. You can choose whichever format that works the best for you. And I got more learning resources for you on Recursion. I'll show you. If you go to the lecture site, and then if you scroll down all the way to the bottom there, and then you will see that we got slides over here for Recursion, which I'm going to go over some today. And also there is some notes summarizing about the recursion problems that we discussed in lectures. And that one there actually summarizes about how you can think about solving problems recursively. I think that could be useful when you review for the exam. And talking about the exam, I'll talk about it in the last 5 to 10 minutes today. All right, please stay until the end, and I'll talk about the exam. And then after the Q&A about the exam format, etc., I will release another PDF by the end of today or early tomorrow, so you can also look at the written form about exam guide. So no information will be lost. Okay, so, and then, recursion resources. And about a review session there, I believe the polling is going to close by the end of this coming Friday. So if you're interested, please do indicate your availability about the review session. Most likely you will be over Zoom, but I'm just hoping as many people can make it as possible. Apparently, I'll try to record the session, right, for those of you who cannot make it. But just go there and then join it and then ask your own question. That might be your best way. All right, any question for me to clarify in general? And as I said, for the exam, I'll talk about it at the end of today. Okay, quick recap. So last time we finished the last bit about inheritance. And so this page over here summarizes about a rule for instance of operator. Just remember the instance of expression here is going to return true if the obj here can satisfy the expectation of whatever class we put here. Or if you look at the inheritance hierarchy, that means B over here is a descendants class of whatever class we want to cast into. Right? So that's the rule we summarized last time. You can refer to the recording if necessary. All right, so this page here is also important to look at other lines as well, line number 1 and line number 3. Okay, I'll leave the review to you. And then we talk about the various scenario where you're calling a method here, and the parameter type over here, due to polymorphism, is going to allow any arguments that's a descendant class of the parameter type, right? That's the essence for understanding this example here. And don't forget, the way we understand it is by call by value, the implicit assignments. Just remember that, all right? Call by value is very important here. And this example here basically is about if you try to look at each one of them, they are not going to compile, right? If you just try the method call, you can try to figure out exactly why. We explained that also last Thursday. The way to make it work, at least for compilation, is by doing some downward casting over here. So it's going to make each one of them actually compile. However, if you try to do downward casting, you always count with the price of potential class cast exception. So it turns out these two will run into class cast exception, but this one here will not. You want to really review about why. Okay, we did explain that in detail last time. And the last bit for this example here, we try to also do some cast over here into resident students, but it simply wouldn't compile. Right? You can go back to the earlier page where I try to summarize about the different categories of the classes. Either the cast will not compile, or it will compile but run into class cast exception, or it will compile and no runtime exception. Right? So these are the 3 categories you want to review. Right? And arguably this is the most important page for you to remember or to really get through about the inheritance lecture. How we can build a polymorphic collection, or in this case, array. If you look at the class declaration over here, we got students array. Each element in the array has the static type students. Polymorphism tells us that when we store the objects dynamically into this array, they might be of any type that's a descendant of students. For For example, if you look at this, look at the diagram we look at, you can see, okay, statically index 0, index 1, they're both students. But dynamically, you can see index 0 point to dynamic type resident students versus index 1 points to an object dynamically non-resident students, right? How exactly we build this array, you want to make sure you review how we build it. And also how you can actually call the get tuition method, for example, on this particular objects versus this particular objects. Dynamic binding tells you that it depends on the dynamic type of the context object here, which can be either resident students or non-resident students. That tells you the get tuition may be called for different version at the runtime. All right, so that's also something you would like to review. All right, I'm pretty sure you will see something like that in the exam. All right. Yeah, another stuff that can also help you will be think about the instance of evaluation, which we did last time, right, for each iteration. All right, take a look. And another one that's also kind of relevant, once you got a polymorphic collection or array over here, we have the so-called polymorphic accessor. All right, so this is an accessor method here that's going to return some value of static type students. Again, polymorphism tells us that if the static type for the return value is students, what can it be dynamically? It can be any of the descendant classes of students. So what we tried to trace last time was, if I try to get S as a return value from get students with index 0, which is going to return this particular objects. Dynamically, it's resident students. On the other hand, if you try this one here with index 1, that one there is going to return the objects from index 1, which is non-resident students. So you can see the same method call with different input values, we're going to get objects of different dynamic types. So when you try s.getTuition here versus here, different versions are going to be called because of dynamic binding. Well, I'm just going to give you the highlights right now. So for the exact details about tracing the code, you will have to review the notes and also maybe rewatch parts of the recording if possible, if necessary. You don't really have to, but if necessary, it's there for you. Okay. And this table here summarizes about the different rules for inheritance. I think it's a little bit dry, I agree, but it's really the best way to be precise about what we have covered. So we explained this one here. I will encourage you to also go over the rest to really make sure you understand everything. Everything we have learned about inheritance are basically summarized over here. So that was the last example we discussed about overriding. So the tricky case you want to look at is this. The dynamic type for this object here is C. So when you say C1 equals C2, we know that it's going to call the version of equals over here. But there is no explicitly overridden version here. So we got to go up along the ancestor. But here we got two versions from the ancestor. We got version number 1, we got version number 2. So which one should we choose? The principle which makes absolute sense in the visual diagram is you want to choose the version in the closest ancestor. So B compared with objects is much closer to C as an ancestor. So that's why we choose that version there for execution. All right, so that's an extra rule you got to remember. But if you visualize it, it makes perfect sense. You should choose a closer one as opposed to a further one. Okay. All right, so that's about inheritance. Any parts you want me to clarify about inheritance in general? Yes. Yeah.
Only work like if B didn't have an overridden method,
That's correct. It could going up. Yeah, exactly. You're basically talking about this case over here. Let's say B doesn't have it, A also doesn't have it. You keep going until you reach the very first one, which can well be the ultimate one in objects. If there's a closer one than the object version there, you choose that one, basically. Or even more. Let's say this is a dynamic type. Let's say you got overridden version here. You got overridden version here as well. Now you also choose this one because that one's closer, right? Yeah, closer just makes sense. Good. All right. And so that's about inheritance. So please review all the notes and also the code example. Reach out to me. I still got office hour this week and next week. Okay. And then we started a discussion about recursion. Okay? And in general, you want to really remember this particular pattern. You remember the PDF I kind of refer you to in the beginning of the class today? If you look at that document there, that one really try to show you that for every recursive problem you're trying to solve, doesn't matter how complicated it might be, you always have to follow this kind of a pattern over here. So look at that and try to get some feel. So if you're given some new problem in the exam, you're going to follow the same principle as well. Okay, so that will be my advice, at least for now. So there are two kinds of cases. You got base case, you got recursive case. For base case, we are simply talking about small enough problem which can be solved right away. You just know what the solution is right away without even computing anything. All right, that's kind of the idea. Small problems. And we'll talk about concrete small problems today when we talk about recursion on strings. And the recursive case will be where you have to make some recursive call, right, programmatically. So given some problem over here, it's simply too big for me to solve right away. So the way I do it is by so-called divide and conquered. I divide the original problem into sub-problems. Each sub-problem is strictly smaller than the original problem. And then this is where the confusion might be when you're first starting to program in recursion. You assume for every strictly smaller problem, I already got solution to them. And then the way to construct the ultimate solution to the original problem is by combining these smaller solutions together. So that's something you want to keep in mind. And then as we solve problems today and also on Thursday, or even next Tuesday, you'll see the same pattern. All right, so programmatically, how can you identify there's a recursion in your program? Very easy. Whenever you're defining some method here, it could be accessor, it could be mutator, doesn't need to be either. Let's say you got some method here, and then you can see the method is trying to call itself in the body of implementation. You know that you got some recursion. All right, there will be some common errors, which I'll point out to you guys a little bit later. But we can do some concrete problem right away before we even talk about common errors. All right, so just remember, whenever you see a method calling itself, you do have recursion. And once you get into the recursion regime, you have to be watching out, okay? All right, and I leave this page clean for you guys. So that one is basically already discussed about call stack, which we talked about back in the exceptions lecture before the reading week, right? So I'll leave that to you. So please review about what a call stack is. And we might need it today very soon to trace. All right, so that's about a recap from last Thursday. Any question? All right, very good. Let's now move on. So today, I can tell you an overall plan. I want to do two problems there about these so-called hello world problems in recursion. Usually when people talk about recursion, they got to talk about factorial and Fibonacci. I got to talk about them first. And then after that, I will move on to a little bit more advanced about recursion on strings. Hopefully we can do at least two problems there, and that will be a nice closure for today. I'll talk about the exam, and then I'll continue with the discussion maybe on Thursday. All right, that'll be the plan for today. Okay, let's take a look. So this is our first problem. It's called factorial calculation. I'm pretty sure you know what factorial is, right? By definition, explanation mark means factorial, right? N factorial will be 1 if n is equal to 0. Otherwise, if n is larger than or equal to 1, you're going to say n multiply n minus 1, n minus 2, all the way down to 1, right? That's a mathematical definition you're familiar with. Let's now be a little bit more critical here. When you look at the solution here, it's definitely one valid way to really express the solution to the factorial problem. But this solution here is not really recursive. Okay, first of all, not recursive. Because in order to calculate n factorial, this one looks like a base case, yes, because it's a very simple case. But this one here is not what we would call a recursive case. In order to solve n factorial, in order for that to be recursive, we are supposed to try to solve another smaller instance of the factorial. But we don't see any instance of the factorial anymore on this side here. So it's not recursive, right? I'm going to contrast for you. So what I want you to also realize is at this point over here, there is no recursive call. no recursive call to the factorial problem. All right. And let's now, I'll give you the recursive definition right away. What will be the recursive definition then? Okay, let's take a look at this one here. Then you can see. N factorial, the same problem here. The base case would just be the same. 1 if n is equal to 0. This here is the same. But now, for the recursive case over here, I'm going to somehow to say, in order to solve this big problem here, which I don't have the solution right away, can I assume I have the solution for the strictly smaller problem? What will be strictly smaller than n? For example, n minus 1 or n minus 2, etc. Once I get that strictly smaller problem solution assumed, I just need to massage that slightly and then get an ultimate solution. So what I meant was, let's say I assume n minus 1 factorial is there. Okay? So we can annotate here right away. So this is the solution to a strictly smaller problem. Especially if you compare n minus 1 and n. And I want you guys to think a bit more abstractly here. Here, the problem size is easily measurable by just n. And I say n reduced to n minus 1, strictly smaller. And we're going to see today about strings. How do you recursion on string? How can you make a string strictly smaller than the original problem? We're going to use a method called substring. And how do you actually say, my input is an array? How do I do recursion on a strictly small array? We need to somehow calculate the subarray. So these are the different scenarios, but follow the same principle. You have to do recursion on a strictly smaller problem. That's the key. Okay, and one more thing, and I'll give you the complete definition. So think about this one here, and this one here. This one tells you that you're making a recursive call. Okay, this one here. Recursive. And the number of recursive calls you have to make does not need to be 1. It could be more than 1. Quite common, I would say. All right, so we assume that we got this solution here. And once I got this one here, basically this part here corresponds to just this part here. I just make it more compact using the recursive call. And then I'm just going to apply another simple computation. It's going to be n multiplied by that. If n is larger than or equal to 1. So that's the complete definition. All right. Again, when you look at this page here, I want you to convince yourself the following. This valid definition here is not recursive because we are not trying to solve a strictly smaller problem in the definition itself. On the other hand, for this definition here, it is recursive because in order to solve factorial of size n, I need to assume I got a solution for n minus 1, which is strictly smaller. And then use it with a little bit massaging, I can get ultimate solution. All right, so that's a recursive definition, which you may have seen before. If you're not, now you see it. Any question about the recursive definition here for factorial? The next step. So I would say later on, I'm going to show to you when we go over serious problems, whenever you want to solve the recursion in Java or in any programming language, you don't necessarily have to go into coding right away. I will highly recommend you try to kind of sketch a few definitions like this. Of course, not exactly like factorial, but conceptually. Sketch some solution based on the few examples you know that's going to work, and then translate them into code later. That'll be a better practice in general. Because as you go a little bit further on your in your degree, the kind of recursion you will be expected to write is not as simple like this. It's going to be much more complicated. So always sketching before you coding. Good. All right. All right. Given that no question here, so I copy this definition here into here. Okay, the recursive definition. What we want to do now is to turn that into Java code. And this piece of Java code has very close correspondence to here. Let's take a look, and then we'll do several things later. You can see that we got factorial. Sorry, I'll make it thinner. Factorial here, factorial here. That's a recursive call. So here you got factorial here, you got factorial here, right? That's a correspondence, first of all. And of course, you got n here, n minus 1 here, n minus 1 here. The base case will be if n is equal to 0, result will be 1. Otherwise, result will be n multiplied by factorial n minus 1, exactly here. Okay? And of course, if you just prefer not to have the result over here, just say return, that's fine too. Just for my tracing purpose, it's kind of easier to see it this way. All right, so the result is going to be reassigned either by the if branch or the else branch, and then we're going to return the result later. Okay. Any question about turning the recursive definition above into the Java code below? Okay, should be quite straightforward, hopefully. Right, so let's now do a little bit tracing. So there are two possible ways of tracing, and you should know both for the exam. Okay, so today I'm going to show you the both tracing methods. One will be to use a more like a high-level top-down approach, which I'll show you exactly what I mean. The other approach, the second one, is to use a call stack, which we kind of did when we talk about the exceptions earlier. I'm going to do that for you, do that together with you about this simple example here. And when we talk about the next problem about Fibonacci sequence, for that problem there, I'm also going to do the high-level tracing together with you as well, just to make sure you're comfortable. But for the call stack tracing, you're going to do that as an exercise on your own. But I will include a video solution to you to guide you through. That one's kind of tricky, but it's important for you to get right. Right? Okay, let's do that. Let's now try to trace factorial 3 in the high level. So what do I mean by high level? Here, you can think about this is the method call I want to start with. Okay, I want to start with this here. And I'm going to put it here. Factorial 3. I start with this. Number one, you can see according to the code, the input size 3 is not equal to 0. So I must go to the recursive case. Right? That one there is gonna that one tells me in order to calculate this, I need to calculate this instead. All right. So that one there, I can rewrite it in this way. It's going to be n multiplied by factorial 3 minus 1, which will be 2. Any question about this step here? That's a very critical step. We're basically rewriting the original problem there in terms of some massaging of a strictly smaller problem. As you can see, factorial 2 here is a strictly smaller problem than factorial 3, right? Because 2 is strictly less than 3. And now, this part is okay. This one contains no recursive call. But this one here, is it a base case yet? No. That means we've got to keep tracing. So if you look at the 2 here, not equal to 0, so we're going to go to here again. So that one there is going to boil down into, and I just noticed that this one here, n should be 3, of course. And this one here should be 2 times factorial of 2 minus 1, which would be 1. Right? You can think about this is the first time we step into factorial. This will be the second time. This will be the third time. All right? The same block of method is going to be executed multiple times. It's a very typical thing you will see for recursion. All right, so this one here, not yet the base case. Still too big. Right? We are not reaching 0 just yet. So what I would do instead is going to be boiling down into 1 multiplied by factorial 0. Let me make some space. All right, any questions so far? So down to here, we know that at some point we should really end. The tree over here or the structure here shouldn't really go deeper and deeper. It should really terminate at some point. So this one here is the base case. All right, I'm gonna color that a little bit so you can see very clearly the correspondence. Okay, this is one method call, and then this is another method call. This is another one here. And this is another one. Okay. In order to do this, we have to make this recursive call. In order to do this, we got to make another recursive call. In order to do this, we just got to make another recursive call. And this one here has reached the base case. That's where we don't make any further recursive call. All right. And how is the result going to be computed? This one here, when n is equal to 0, we know that it's going to match this case, and result is going to be assigned to 1, so we're just going to return 1. That's the base case, right? So what I can do in the high-level tracing here is, sorry, let me just undo that. So this one here, we know that it's going to be just 1. And once we are done with this, we can now move on to the last one here. So factorial number 1, according to our definition, should be 1 multiplied by what's just returned. 1 times 1. So that one there is 1. And what about factorial of 2? It's going to be 2 times 1, which will be 2. And then ultimately, factorial 3 is going to be 3 times 2, which will be 6. So 6 will be the final answer we are expecting. So this is like a high-level tracing. You basically start with the original method call and then follow through the base case versus recursive case definition in your method and go all the way down to when you reach the base case and try to get the result from there. Okay. This is only the first one. I'm going to do a few more with you today and also on Thursday. So you definitely get an intuition afterwards. All right, any question about this kind of tracing? Yes. Not necessarily. So I think a recursion, we don't really focus more on the efficiency here, but I think a recursion sometimes it may take more memory, but there's a way to optimize your recursion. It's called tail recursion, but we may not talk about it until maybe 2101. I would say when you are developing your own projects, you definitely have the freedom to choose between recursion and also loop. Sometimes you might find it easier to design your solution using recursion. It might be. Now it may not be possible, right? You might seem recursion very confusing, maybe. But in the long term, recursion actually works pretty well for certain problems. It's just much harder to do certain problems using loop instead. Yeah. Good. All right. Yes. No, factorial, feel free to solve in a loop. I'm pretty sure you can do it. That may be more like a first year level question, right? So that's why I don't even mention. So for all the problems that we talk about in the recursion lecture, they are all solvable by loops. In a more general level, the expressive power by recursion and by loops are equal, meaning that there's nothing that you can solve using recursion, but you cannot use loops and vice versa. Recursion in some way, I would say, whenever I think about it, think about recursion, I don't really worry too much about efficiency, about space. I always think about to solve my problem correctly, which thinking paradigm is better for me. Should I think iteratively or recursively? For things that I can think more naturally recursively, I should definitely go for recursion because it's a guarantee for correctness. Because ultimately, when we go to 2101, the efficiency for like how fast your program can run is not the first priority. What's the first priority is correctness. If a code runs super fast but it's wrong, useless, right? Yeah. All right, good. All right, so let's now try to see how the actual execution is going to occur, right? Let's now do this quickly. It wouldn't take so long, but we got to focus, okay? At least I need to focus, okay? Let's now talk about how we can do that. And once we have done that, I will give you some exercise to try in a moment. So what we do is we're going to execute factorial 3 to start with. So we're going to have factorial 3. Push that onto the stack. And this one here, let me annotate right away. You can think about this one here corresponds to the top one. So think about the way the high-level tracing is going to go is go from top down. And the way we do the tracing using a call stack will be bottom up. All right, something like that. So we got factorial 3 here. And then So the input n is now 3. Put it here. Okay, 3. And it doesn't really match the base case, so we're going to bypass it. And we're going to go here. So that will be 3 multiplied by factorial of 3 minus 1, which will be 2. And this will be the first recursive call we're going to make, which will be factorial 2. So I'm going to put factorial 2 over here. All right, so that one there, you can also see that one corresponds to factorial 2 over here. All right, so far so good. And let's now try to execute factorial 2. So n will be 2 right now. We're executing the same block of code for the second time. The base case has not been reached, will not be reached. So we're going to get 2 times factorial of 2 minus 1, 1. So this factorial 1 is going to correspond to basically here, right? And to execute it, we push that onto the stack. So factorial 1. All right. And then let's now try to look at, is factorial 1 the base case yet? Not yet, right? In order to reach a base case, it got to be n equal to 0. So let's do one more. Almost there. 1 here, and that has not reached the base case, so we're going to do one more. So it's going to be 1 multiplied by factorial of 0. And that one there does seem to be the base case. Factorial 0. And then I'll put factorial 0 over here. And there we go. Right? You can see exactly the opposite order corresponding to, right, between the two methods, right? Now, factorial 0 here is going to match the base case, right? Let's now do that. So this one here, we got 0. And then 0 here is going to match. So we're going to get the result. That's going to be return. The way to trace this would be, you got to remember this return result somehow is going to be handled by the Java runtime, which we don't need to trace too much. You just got to say, I'm going to pop this off from the stack. That one's going to return just 1 because of the 1 over here. Okay. Also, you can see factorial 0 over here is actually 1 because, let me do another one. When we are done with this one here, it's going to return 1, which means this one here is going to be 1. At the same time, the next one to execute will be factorial 1, right? Remember, last in, first out for the stack. So now we're going to do factorial 1, which is going to correspond to this particular computation, right? That one there is going to be 1 multiplied by factorial 0, all right, which is here, right? You can take a look at that one too. So we got 1 here, that's return, and then the whole thing for factorial 1 is going to be 1 multiplied by 1, which will be 1. That means this one here is also going to return 1. All right? When this returns 1, what will be the next one to execute? Factorial 2, right? Factorial 2 is over here, which will be 2 times factorial 1, which is exactly this return value here. All right? So that one there, bear with me. That one there is going to be here. And I know that this one here is also 1. So 2 times 1 is going to give me 2. That tells me this one here is going to return 2. All right, almost there. Once this is returned, the next one to execute will be factorial 3. And that one there, by definition, is going to be 3 times factorial 2, which is returned as 2 over here. So let's now do that quickly. So we got factorial 2 is 2. And then we know that factorial 3 is going to be 3 times that return value, which will be 6. That means this one here is going to return 6, and that will be the ultimate value that's going to return from the Java execution. Right, so when you study there, I would suggest before you even attempt the exercise I'm going to assign to you, try to understand exactly how this has been traced and see how the method is being executed in different places. All right, that's important. Yeah, in the lab session tomorrow, that'll be the last day for the lab session. In the morning, I need to invisualize some makeup tasks. I cannot really be doing any demo, but maybe in the afternoon, I can do potentially 2 things. I can maybe try to show you guys how to trace some simple recursion using Eclipse, right? And also I can maybe go over with you some extra problems on recursion. That's what we can do. All right, for tomorrow afternoon. If you can make it, come, and then we'll talk about recursion. All right, any question about tracing? Yes. Mm-hmm. Yep. It's definitely possible. So yeah, in the exam, you might be asked about code tracing. Specifically for recursion tracing, you might be asked to maybe trace this way here, the high level, top down, or you might be asked to trace using a call stack bottom up. So I'm going to assign you the exercise to do. You can also try that. That'll be the best way to prepare. Yeah. All right, any question about factorial? Good. The next problem about recursion, before that, let's talk about some common error. All right. So take a look at this version here, which is kind of intense to calculate factorial. This one here, you can see we got original problem n, making a recursive call n minus 1. Seems to be okay. But is there any error you can identify here? Quite obvious. Go ahead. No base case. Yes. All right. And let's think about what's going to happen here, right? If you try factorial 3, for example, it's going to boil down into n multiplied by factorial 2. And then it's going to be 2 times factorial 1, and then 1 multiplied by factorial 0. In the correct version that we just went over, since we got a base case, it's going to stop right there without going any further. But now, since we don't really have any base case, so it's simply just going to say this one here, 0 multiplied by factorial minus 1, and etc. It's a very typical case of infinite recursion when you don't have a base case. Okay, infinite recursion. All right. All right, let's now move on to the next one. This one here is kind of the opposite. Well, since I said you didn't have a base case, well, there you go. You have a base case. When n equal to 0, returns 1. It's a correct base case. But can you spot any other error here? I don't do n minus 1, but to be more general, whenever you're doing a recursive call, you want to make sure the problem you're trying to solve is a strictly smaller one. Right? So this n here is just equal to n, which is not good. What's going to happen is like this. I'll make it a little bit simpler. If I want to calculate factorial 1, that one there is going to calculate n multiplied by factorial 1. That one there is also going to be n multiplied by factorial 1. So you never try to reduce the problem to some base case. Also similar, infinite recursion. Okay, similar. Yeah, error number 1, you might be missing a base case. Error number 2, you have the base case, you do try to make some recursive call, but for the recursive call there, some of them did not try to reduce the problem size. All right, that's something you want to remember. Good. Okay, let's now take a look at the second problem for recursion. Okay, it's something called the Fibonacci sequence or Fibonacci number. Maybe many of you have seen this before. If no, let's now take a look at the pattern. Very easy to identify. The definition for the pattern goes like this. The first two items are always 1 and 1. Always. Start with 1 and 1. And we kind of refer them to as F1 and also F2. So the indices in this sequence here starts with 1, not 0. Okay? You can think about maybe these two are so-called base cases. You can think about, right? 1 and 1. After this, the sequence has a special property. If you look at any number starting from position 3, for example, this number here, the value of it is the sum of the previous two numbers. For example, 21 is equal to a plus 13. 89 here is equal to 34 plus 55, right? You can see the pattern here. Or to be even more explicit, if I look at 21 here, for example, right? This one here, you can see 1, 2, 3, 4, 5, 6, 7, 8, right? It's the 8th number. So this one is F8. That one there is exactly equal to the sum of the previous two numbers. And this one here is F7. And this one here is F6. Right? F8 is equal to F6 plus F7. Right? So that's a very easy to understand sequence here. Of course, if you want to solve it, you can use a loop. Nothing wrong with it. But its definition there is inherently recursive. All right? Let's see. Let's say I want to calculate, for example, Fibonacci of 4. Let's say. By definition, it's going to be the sum of F2 plus F3. The sum of the two numbers that come before F4. And F2 is already a base case, agree? So that one there, we know that it's a base case. 1. F3 over here is not yet a base case, so we got to go further. And this one here, F3 by definition is going to be F2, also F1, the sum. You can see both of them are base cases, F1 here and F2 over here, right? They're both base cases. So you can see F3 here is actually 1 plus 1, which will be 2. F2 here is 1, and 2 plus 1 will be 3. All right, so this is what we have been calculating. So this is the F4. And think about F2 is over here. F3 is over here. Right, that's just another example here. And you can see the way I kind of trace the calculation for F4, just like the top-down approach I did for factorial. So that's why I said to really understand the recursive solution in a high level, you may want to go for approach number 1. Okay? Approach number 2 is something fundamental. You may not use it in practice, but you also need to know. All right? All right, guys. Any question about number 1, the definition for Fibonacci number, and number 2, about this level tracing, high-level tracing here? Any question? All right. What I owe you guys now will be the recursive definition for Fibonacci number. So you can think about f of n here. So we got two base cases. It will be 1 if n is equal to 1. It will be 1 if n is equal to 2. Right? Exactly these two base cases. And it will be when n is larger than or equal to 3, f of n minus 1 plus f of n minus 2. So think about n here, also n minus 1 here, n minus 2 over here. This one here, strictly smaller than the original problem. This one here, also strictly smaller than the original problem. And we got two recursive calls. Two recursive calls. All right, so that's a recursive definition for Fibonacci number in the sequence. Alrighty. All right, so now let me tell you the exercise you can try to really sharpen your skill about tracing. I'm going to leave this page clean for you, so you can see the recursive definition here. All right. I want you to trace number 1, Fibonacci 4. But that one there, for a top-down approach, I already did it for you. Okay, but you can try it again, no problem. And of course, you can look at the correspondence here. You can see Fibonacci number n. In the recursive case, is simply Fibonacci of n minus 1 and also n minus 2. It simply corresponds to these two. Right? Very easy to see correspondence. What you really want to do as exercise is, how do you trace Fibonacci 4 using the cost stack? It's maybe much more trickier than you might think. All right, so I'm going to encourage you to try this one here. And then by the end of today, when I release the lecture recording, I'm also going to include some pre-recorded video to walk you through the solution. All right. So this will be something I will assume you have done it before the exam. Okay. That's important for you to know how to do. Yes. Yeah. Good. Okay, I can answer that. It's a very critical question here. Very good. So your classmate was asking, when I try to trace, for example, if I got Fibonacci 4, I know that it's going to be conceptually 3 and 2. The order, like a short circuit, is going to be from left to right, meaning that you have to complete this one first before you can complete this one. Now, think about it this way. In order to calculate this one here, I need to make sure this branch is done before I can ever start with this branch. That's something that's a key when you do the tracing. Okay. Yeah, guys, give it a try. If you really kind of try by kind of get stuck, that's okay. At least when you look at the video, you'll appreciate more about the correct way of tracing it, right? All right. Good. That's about Fibonacci. Any question? Okay, I think we're doing well. And maybe doing well, we can leave more time for you to ask questions about how the exam is going to be structured. That'll be to your advantage. We'll see. Okay, before we take a break, now we're done with the hello world problems for recursion, Fibonacci, and also factorial. And before I introduce the problems that we're going to solve on the string for recursion, let's now understand some critical methods, mainly the substring method in string class. It's a bit tricky, but I want to make sure you're okay with it. Okay, so here we got a tester here, and then we're going to call the method called substring. Substring here. There is another method there called character add that might be also useful as well. And before that, let me just mention some tip over here. You may want to understand string as an array of characters. So for those of you who might be taking a 2031 or 2032, I'm pretty sure your professor told you that string in the Java, so not in the C, is like an array of characters, right? Similar here, conceptually. Okay, so let's say if I got S, simply, if I say S is equal to, is assigned to hello, for example. Diagrammatically, think about it's an array of size 1, 2, 3, 4, 5. We got 5 characters. 0, 1, 2, 3, 4. And then I got H, E, L, L, O. Each one of them is a character. All right. And one thing to note, the first index should be 0, always, like an array. And the last index here should not be too surprising to you. It should be the length of the string minus 1, right? Which will be as the length. And notice I got to put a parenthesis because it's a method call. All right, minus 1. All right, that's the basics you should know. All right, talk about substring. So here, whenever I say s dot substring, okay, let's say I got I here, I got j over here. You need to pass 2 inputs, like integers, I and j. It's going to collect all the characters between certain range specified by I and j. I'm going to tell you what the range is. And then you're going to make all those characters in the range as a new string. Could be the original string or could be something shorter. Okay. So this one here is going to form a substring by collecting characters in this interval. So this is a mathematical form. It's going to be from I until j exclusive. I'm sure you have seen this in the calculus course, right? So this means closed interval, and this means open. That means j value there should be excluded. So this will be as if I said from I until j minus 1. That's equivalent. Okay, let's now take a look at some example here. And typically, I should be less than or equal to j. For example, I want to take a substring from 1 to 4. I wouldn't say from 4 to 1 typically, but you might have something like that, which might mean something different. Well, let's take a look at the first example here. 0, 0. According to our definition, it's going to be from 0 to minus 1, right? Now, this is the exceptional case you have to, well, when I say exceptional, I don't mean exception will be thrown. Special case that you got to handle. Whenever you got the I that is strictly larger than j, which is not the typical case, right? When I is strictly larger than j, that means you want to return an empty string. Because there's no character that will be between 0 and minus 1. No. So empty. All right? So this one tells you I larger than j, that means empty string. That's a special case you have to know, all right, for substring. And this one here, 0, 4, that's going to be between 0 and 3 inclusively, right? So that's going to be, let's see here. We got A, B, C, D. So index 0, 1, 2, 3, right? So that'd be from 0 to 3. So A, B, C, D itself, all right? And then if you got, for example, 1, 3, so that'd be from 1 all the way to 3 minus 1, 2. That one there is going to be 1 to 2, BC, over here. Finally, if you try the substring concatenation, that one will leave to you as an exercise, right, to see exactly how to work it out. Okay, for substring. Any question about substring? Yeah. You will get conceptually, yes, something like that. But I think you will get a slightly different exception. I can look it up and let you guys know next time. I think there's different exception name. Is it like a string index out of bound or something like that? I need to look it up. Yeah. There will be some exception if you pass maybe an index that's either too small or too large. Indeed, yes. All right, one more thing. I want to make a remark for you guys to think about. I'm going to state the facts. You guys can think about why. Okay, I'm going to put it here. For any given string, how about non-null? So you don't need to worry about the null case. And then given integer I, just one variable I, such that I is a valid index for getting a character from the string. Let's say I and then s the length minus 1. All right, it's a valid index. So we got basically s, we got I. So there is a way, just for like a property purpose, there is a way to reconstruct the string s by splitting it into two substrings. All right? Think about it this way. I'll put it down first, and then I'll visualize that for you. Just a moment. So let's say we got s dot equals, and then I'm going to put some expression here, which is going to be a string. And I'm going to concatenate two substrings over here. The first substring is going to be computed using s dot substring. Okay, I'm going to put something here. Also s dot substring. Here. All right. And then, okay. Oh, I might want to leave more space over here. Okay, first of all, the beginning index should be 0. The ending index should be s dot length here, because it's exclusive. So I cannot say minus 1, right? If you put the s dot length over here, it's going to make sure it's only going to go up to s dot length minus 1, right? Okay. Okay. And now I can simply put I here and I here. It's property that's always going to be true, meaning that equals is going to be true. Very easy to prove this visually, what you justify. Think about this is a string, character array. We start from 0. We go all the way to s.length minus 1. So that's why you can see s.length plus 1. Sorry, it's this index here plus 1, so that's excluded, right? So we still go up to including this index here. And then I'm saying the following. If I choose an I in the middle here, this part over here is going to go all the way, but excluding I. And this part over here is going to go all the way from I until the end. That's a visual justification, which we're going to do a lot in 2101 next term, if you take the course with me again. All right, we'll see. All right, so that's something you can think about. Okay, that's a nice mathematical property to always kind of reinforce your understanding. Good. Okay, I would suggest we take a short break by taking attendance. After the break, I'm going to spend about maybe 10 minutes or so going over 1 or 2 recursion problem on the string, and then I'll talk about the exam. Okay. Let me pause the. All right, so we're gonna go over 3 problems in total. We may just go over the first one, I guess, or maybe second one a little bit. But we're definitely gonna finish that on Thursday, and then on Thursday we also need to learn about how to do recursion on arrays. All right, that's something we need to learn too. All right, the first one here. Do you guys know what a palindrome is? Okay, by definition, a palindrome is a word, a string that will read the same forwards and backwards. All right, so for example, one moment, sorry. Is empty string a palindrome? It is, right? Empty string, read the same forward and backward. Also, if I have a string of a single character there, that's also a palindrome because A reads the same forward and backwards. And what about madam? Palindrome, right? Okay, you can verify yourself. Madam, if you read it forward, left to right, and right to left, just madam. How about race car? Okay, that's also a typical one. Okay, how about man? Apparently not, right? So it will be man forward, nam backwards. Okay, I got enough idea. One thing I want to point out right away. When you are trying to design a recursive solution to some problem you may not have seen before you can sketch any idea, this will be the very first step. You want to go over simple and reasonably complicated example at the same time to see what the output should be, right? You can only get some inspiration if you have enough insights or understanding about the example. So always go over some example, which I'm trying to do right now. Okay, and then in those examples, there will be the so-called base cases. You can see typically if you're doing a string, empty string is a very popular, like a base case, or maybe a string with a certain very small length, like a length 1. So these 2 are the base cases. Other cases will be considered as way too big for me to solve right away. Those are the cases I need to think about how I can somehow divide the original problem into sub-problem that's actually strictly smaller. All right, let's now focus on this one here. Okay, palindrome, that's the first problem. Let me give you some insights about the problem, like the solution itself. And then to see if you can kind of see the procedure of deriving the recursive solution. If I think about a race car over here, it is a palindrome. If I try to read it forwards, the first character I will see will be R. And if I try to read it backwards over here, I'm going to see the first character R as well. So this one kind of tells me, if I kind of imagine that, I'm trying to read forward and backward at the same time. I'm basically comparing R and R, A and A, C and C, and etc. Right? That's basically what forward and backward really works conceptually. That's insight number 1. Insight number 2. Let's say I am trying to, let's say this one here. Let's say take this string, for example. If I still try to do conceptually reading forwards and backwards, the very first character I'm going to encounter will be A here when I read forwards, and S over here when I read backwards. As soon as I see that this character here and this character here, they are not the same, do I really need to read forward anymore? I don't need to, because there's no chance they are palindrome, right? This tells me insight number 2. When I try to read forward and read backwards over here, as soon as I see the very first pairs of character, they are different. I should stop right away and tell you that it's not palindrome. On the other hand, when I see the R and R over here, they are the same. That doesn't really mean it's going to be a palindrome ultimately. At least I have a chance to reach a palindrome. All right. So these are kind of the insight I can see right away from the examples. All right. So given this, I'm going to give you guys some visual hints. All right. So think about here, right? And then over here. Let's take a look at this one here. So the way to really design a recursive solution is, I know that I should somehow get a strictly smaller problem in order to recur on. What can be a strictly smaller problem? I know that if I already have read R and R over here, and I know that these are equal, so I do have a chance that this strictly smaller substring here may be a palindrome, or maybe not. I'm just going to run through the same procedure to, again, compare A here and try to look at whether the middle part is also palindrome, and so on. So the way I'm extracting the strictly smaller problem is by getting rid of the first and last character here, and then see what's the middle. All right, that's kind of the insight into coming up with a recursive solution. So here, this one sounds pretty straightforward, but I do want you to remember, when you want to come up with a recursive case, always think about what kind of strictly smaller problem am I going to derive from the original problem. That's the key. All right, strictly smaller problem. So imagine that I'm trying to program a Java method called palindrome, is palindrome. And I'm given the string race car. That's what I'm given. All right. So what I will do is I'm going to somehow compare the first character and the last character over here. And then I'm also going to assume I got a solution to whether or not this particular strictly smaller or strictly shorter substring is a palindrome or not. So what I really meant by was this one can boil down into R equals R, and I have some solution to the strictly smaller problem, which will be is palindrome, and then I got EECS2030E. Right? You can see this one here compared with the original string is a strictly shorter, strictly smaller problem. And of course, this one here might require further recursion, but understanding the first step here is important. Right? One more thing before I show you the Java code. Just remember, the critical thing is to look at the original string here. That's too big for me to get a solution right away. You want to think about how can you get down to some strictly smaller problem. For palindrome, I just get rid of the first two characters here, and then this will be everything that's left from the two characters removed. So that's a strictly smaller subproblem here. Okay. All right, that's now, okay, I think that will be it. I can go over the solution with you quickly and do one tracing, and then that'll be it. I can continue from Thursday. Just finish this example here. So this is Java method, is palindrome, returns a Boolean, and takes a string. And the base cases will be when the string.length will be 0 or 1. You just return true. All right, that's the base cases. And the recursive case will be, we get the first character and last character. So at index 0 and at this particular index, the last index, right? First and second, and the middle will be here. So think about what we're doing here is, if you got your original string over here, think about this is the first character. And this one here is the last character. And this one here is the middle part over here. Right? You want to convince yourself that this substring expression here is really corresponding to this one here. All right, that's something we covered already before the break. Okay, I'll leave that to you. And then we're going to return a single expression here. So it's going to be the first character equal second character. And remember short circuit evaluation, meaning that if this is already false, I don't bother to go any further to the right-hand side. I will only go to the right-hand side if this is already true. All right, just remember short circuit evaluation. Okay, let's do some very quick tracing just to show to you. And then I'll talk about the exam. Okay, let's do maybe a shorter string. So we don't need to do a very long string to try. But I'll give you some exercise to try. So why don't we try is palindrome. Okay, let me just, okay, how about this? Is palindrome, why don't we say A, B, C, B, A. Okay, it's a palindrome. This one boils down into, okay, we got to do ampersand calculation, right, over here. So it's going to be first character, A and A equals A, and then is palindrome, the middle part will be B, C, B, right? Okay, let me use a different one here, B, C, B. All right. And this part here, we can definitely calculate. That one there we know is true. So, because of short circuit evaluation, we can now proceed to the recursive call. So this one here, we're going to look at B and B. So boils down into B equals B, and also is palindrome C. All right, you can see the C here is in the middle, right? And this one here is indeed one of the base cases, right? When the length is equal to 1. This one here is going to give us true. And we know that this one here is also going to give us true. So true and true. So I forgot to put ampersand here. All right. So true and true, that means is palindrome BCB should be true. And then what about is palindrome the bigger problem? It's going to be this part here and this part here, which we know already true. Overall, it's going to be true. The high level tracing here is much easier to manage. You just got to practice a little bit more. All right. Okay, exercise for you. Okay, I'm going to write it down. Try the following. Number one, why don't you try the race car example? Okay, it's palindrome, race car. Okay, another example you should really try to trace is palindrome how about this? All right, give a try to both. All right, exercise number one, exercise number two, to do the high level tracing. And on Thursday, we're gonna go over another two recursive problem on the string, and then we'll move on to array. All right, let's now talk about your exam. All right. All right, so yeah, for your exam, I'm pretty sure you know the time and the date. So it's gonna be not a coming Sunday, but a Sunday after. Okay, 10 a.m. to 1 p.m. And then this is where it is. If you don't know, look at the map. It's pretty close to Lausanne, actually. So the format, mostly it will be written question. Okay, so what do I mean by written? Could be, I'll just give you some major examples. Okay, mostly written. It could be, for example, some explanation. Could be some justification. And also could be definition, could be. And could be some tracing output. And also could be some coding question. I'll talk about them one by one. So explanation and justification is similar. So if you, just for example, if you recall, there was one question there on the written test number 2. I gave you like a several option for console tester and JUnit tester, asking which one should be valid, right? Like appropriate. I might just give you one option in the exam and ask you to tell me to judge whether or not that particular console tester or JUnit test is valid or not. Give me the reason. Right? You got to write it down. Or I might give you some variable substitution and then ask you whether or not it will compile. Or maybe I'll give you a code fragment and ask you, are we going to get into class cast exception, right? Kind of explain. And definition here, yep. So go over the basic definition. For example, what is single choice principle? What is cohesion? What is aliasing? Things like that, okay? There might be some tracing output, so I might give you a piece of code, and I simply want you to tell me what's going to happen at the runtime. So you might tell me there might be some exception thrown, or the code doesn't even compile, or maybe it will compile but run into some assertion failure, right? You're going to do the tracing on the paper. And the coding here is not going to be to the extent of your programming test, not really, right? It's afterwards more like a paper and pen test. So coding here, I would say, you might be asked to write some fragment. I want to remain a little bit vague over here. What do I mean by fragment? It could be, for example, I might give you a fragment of code, large one, and blank out several lines, want you to fill it in. Or it could be that I want you to program a method. I'm pretty sure there will be a recursive method, or one or two, at least one. So there will be at least one recursive method question. And your safest bet is to really go over, let me point out to you again, you can definitely start preparing today. You already have a very good foundation about what a recursion is. You just need to practice. If you go to the lecture site, you will see that so this one, okay, I forgot to point out to you in the beginning. So this is a lab that I gave to also 2030 last time when I taught the course. So this is a lab also about recursion. So I got a question itself and also the solution. Okay, make the best use of it. You want to look at the solution directly, not so recommended, but I'll leave it to you. Right? Anyway, so that's something you can definitely make use of. Also for coding bet, I mentioned last time, I think especially coding bet part 1, that one will be the more basic recursion problem. Okay, and you'll be also beneficial if you can try some of the recursion 2 as well, but focus more on recursion 1 to begin with. And so this is source code from the example we discussed in class. Okay, so that's about recursion. All right, so the way I'm going to make question myself about the exam will be I'm going to go over the slides and also my own iPad notes that I released to you. I'm going to look at over each page, and if there's any page that catch my attention to say, oh, I should really ask you guys something about it to test your understanding, so I will do it. So your safest bet, just go over everything we have covered. So anything that you might see in the exam will definitely be something that we already cover in the course. That one's guaranteed. Okay. All right, coding bet here, and then no data sheets, you don't need it. And for sketch paper, so there will be one question booklet handed to you. You gotta fill out your name and make sure you return the question booklet. I will also give you an answer booklet with all the blank pages. You must clearly identify the question number you're answering, and also you can maybe do some sketching at the end. That's fine. As long as it's clear which part of your answer should be graded, that'll be fine. So don't bring your own sketch paper. You will be provided some. And please make sure bring your physical ID, just easier for us to check. We're going to ask all of you to put your mobile phone in the back and put it underneath the table. No mobile phone on your table. All right? Please make sure bring the physical ID. And if you want to bring water, you want to bring snack, not a problem. All right? Okay, we have time, so now I can answer your question, and then let me know. Go ahead. Yeah, I would say, okay, the labs in general, you don't really have to redo all the labs. I don't think so, okay? So for each individual lab, you want to focus more on maybe the more critical methods, like how we do them. If I ask you just to program the critical method, you will be able to do it. For lab number 5 specifically, 2 things over here. So lab number 5 itself, once I give you the solution, you can go over them, make sure the critical methods are understood. And for abstract classes and interfaces, it will be just like another lecture. So you want to make sure go over the slides. If I test you any knowledge about it, you are able to answer. Well, I would say, how about this? There's 100% there will be question on inheritance. There's no way I'm going to skip that on the exam. But there will also be maybe some question related to basic OOP. I wouldn't say like how many percent. So I think your safest bet would be definitely since the inheritance is actually newer idea, you want to review them first, make sure you're comfortable, and then go back to what you study for the written test number 1, written test number 2, and anything's possible on the exam. Yes. Not really to reflect exactly what will be on the exam, but I will give you some example question. You can get some idea. Yeah, just give you some. Yeah, exactly. So I think, because if I give you some example question, they will not be the same, compared with the actual exam. So your safest bet will still be to go over the materials. Yeah. Question. Sorry. Sorry, say it again. I didn't catch you.
So for the tracing output type of questions,
Yeah.
are we going to be graded on like how we display our work, like your
Yeah, okay. So if you are to do tracing for the exam, we're not going to grade any intermediate work you have. We only care about the final answer. All right? For the tracing. Yeah, okay, for coding, yeah. So if you only got some very minor syntax error, for example, if you forget about a semicolon, if you're supposed to call a method, let's say add point, but you say add points, that's fine too. We will judge, yeah. I can answer more, guys. Okay, if you need to go, that's okay. Please be quiet. I'll just try to answer more questions. Go ahead.
Will we have to write any of the various diagrams that we've gone through, or just be able to read them?
The what? The
Like various little diagrams, like the stack one and the array one. Like, will we have to write our own version of those?
Yeah, you may have to. So how about this? For the diagram, the question itself will be very explicit about what you should do. Yeah. All right. Thank you. I'll see you on Thursday.